In this video, we will discuss about on a topic is engine airframe integration aspects of hypersonic vehicles. So, is hypersonic vehicles, before we go into this video, we will know about what is the aircraft speed categorization. So, depending upon the mag number, we categorize the aircraft vehicle is subsonic speed, transonic speed, sonic speed, supersonic speed, and hypersonic speed. So after that, the Mach number is greater than 5. That is called, that's all called is a hypersonic aircraft. So the approach of the German hypersonic technology program is introduced in the year of 1988 to 1995, and schedule of German hypersonic activities in German efforts dedicated to these key technologies were initiated during the 1987 period to the 1995, and they were undertaken by the international cooperation within the German hypersonic technology program. After having performed extensive system concept study work, the decision was made to the select as a TSTO concept is a leading reference concept of the development of the above listed key technologies in three major time frames. So at the end, mainly to shortcoming of the national budget, the program was transformed as a starting point to an ES and initiated of international European program named FESTIP. It's a future European space term protection investigation program. The key problem is indicated is in engine airframe integration. The most important problem for the integration of an air-breathing engine with an airframe designed for horizontal takeoff and capable for flight up to supersonic hypersonic speed is a sufficient large positive overall thrust to minus drag balance for the acceleration of the vehicle. This requires a maximum of engine thrust performance, a minimum of engine frame integration losses, and the vehicle aerodynamic drag reduction with high prediction accuracy. This requires validated numerical computational tools and therefore experimental facilities for the simulation of the flight environment on ground. Both requirements are not easy to achieve even in present time. Therefore, the proof of successful engine airframe integration has led to many proposals for in-flight demonstrator concept. Example is thrust and drag concept. And the next of the aerodynamic engine airframe integration, the next view graph shows symmetrically the major aerodynamic forces acting on aircraft with an integrated air breathing engine. There are very high forces at all engine components, and the resulting net thrust to accelerate the vehicle against the aerodynamic drag is a small difference of nearly equally high numbers. This becomes specifically true at transonic speeds. There is a high sensitivity with regard to nozzle aircraft body integration into intake installation and the real gas effect at hypersonic speed beyond the Mach number 5. The task for of engine this airframe integration of a turbo ramjet propulsion concept. The engineering task for the optimum engine airframe integration will be briefly discussed at an example of a turbo ramjet propulsion engine concept. The reasons for this choice of engine concept will be outlined later. First, on the engine side, the variable air inlet, the fuselage nozzle extension, the engine cowling, and the boundary layer management are the most important engineering tasks. Second, on the airframe inside, base drag for body flow and preconception, thrust vector definition and control, and the fuel supply system have to be investigated. And third, overall resulting performance and thermal analysis of the overall systems has to be performed. This leads to several mostly iterative loops and hopefully finally to a converged system concept fulfilling the design missing requirements. So this air breathing system is integration for Different types of aircraft accomplishment of the major characteristics of alternative integration types is given by comparing the most important pros cons in this table. The Concorde as well as SR-71 are both restricted to relative low supersonic Mach numbers. This is mainly due to the missing precompression effect of the aircraft fuselage after body nozzle expansion ramp. But on the other hand, the asymmetric afterbody expansion ramp produces a high influence on the pitching moment of the whole vehicle, which has to be controlled. This leads in most cases in additional trim diagram will be discussed later in detail. So thank you for watching this video. Thank you.